Good afternoon, everyone, and welcome to the Potter webinar featuring FFE Lineaer Heat Detection. Dean Russian's going to be presenting today. We'll let you all know that I have your microphones muted and your cameras turned off. If you have any questions during the presentation, please add them to the chat box. We'll take several breaks during the presentation and read those questions and make sure that everything gets answered. Thank you very much, and take it away, Dean.
Thanks, James. Thanks to Potter for hosting this. Welcome, everyone. Today we're going to be talking about FFE's Linear Heat Detection product, as well as many different applications, real-world examples, code guidance. As James said, I'm Dean Russian, been with FFE for 3 years. I am the applications engineer for the Americas. What we're going to go into in the presentation today, a little bit about FFE, the company, if you haven't heard of us before, and where you might know us from. We'll dive into linear heat detection, all the who, what, when, where, and whys as it relates to the technology, various application examples and real-world examples from the field. And we'll also be providing a comprehensive overview of our 2 different product versions. Those 2 versions being fixed temperature and programmable temperature. The FFE product is a little bit different than what's available by the most well-known brand that everybody knows on the market. Some key differences there, which we'll be talking about. We'll also go over some design best practices as well as some ITM related testing procedures and things like that. As James said, any questions, feel free to put them in the chat, and we'll take a break or 2 throughout the presentation to address those. And also, we do have a few slides on elevator shafts in case that is a topic of interest, which James mentioned might be. So FFE company history. We were founded as Firefighting Enterprises, 1974. So we hit our 50th anniversary as a company. We started by manufacturing halon fire extinguishers, many of these for the aerospace industry. Then around the 90s, early 2000s, restrictions, the way that they were regionally around the world, caused us to do a pivot more to detection. We were also acquired by our parent company, Halma. So we offer as a specialty detection manufacturer 3 different product lines of specialty detection. That's beam smoke detectors, optical flame detectors, as well as linear heat detectors, which we're talking about today. So throughout the 2000s, you can see some key events that happened, different product launches. We have a test facility in the United Kingdom where all of our product is manufactured. Also, we've recently launched a new beam smoke detector, and it's been within the last year that we launched this linear heat detection product line. Just to help visualize what FFE looks like in the diagram of our parent company and sister companies. Here we are, FFE on the left, manufactured in the UK. Our 3 different product lines here, ProReact, FireRay, and Talentum. Today is all about ProReact. And then a few of the logos of some of our sister companies that deal with life safety, fire suppression. We also have a wide range of different technology companies across medical and different electronics, some software mixed in there as well. There's over 45 companies that we are sister companies with, and we do collaborate with several of them. And Halma companies, in total, over $2 billion annual revenue. Mission statement for Halma is to grow a safer, cleaner, healthier future for everyone every day. And FFE's mission statement, specifically since we deal with life safety, we exist to ensure that all lives and livelihoods are protected from fire, even in the most challenging environments. So we do take that seriously and try to have that be the theme for all of our conversations. And many of the people that we work with, that is also their goal. So we'll get right into linear heat detection. And how does linear heat detection work? The first type, this is in reference to the fixed temperature variation of the product. This is the one that's been around for many, many years, most commonly known. It's also referred to sometimes as short circuit sensing. And what it is, it's two conductors separated by insulative plastic or a polymer. So it looks similar to just a fire alarm cable. You have your two core conductors. You have an outer jacket material that's going to protect it from all of the different elements in an environment. And then the insulative plastic or temperature sensitive polymer is what separates these two metal core conductors from one another. At normal temperatures or at your expected ambient temperatures, these two conductors stay separated. So in this cross-section view, this would be the equivalent of an open circuit. This would be the state where you have an end-of-line resistor, for instance, and your resistance value would read the end-of-line resistance plus whatever the resistance of the cable is. So that's normal operation. Now, as the temperature is increased, as we move down in these cross-section views, you see as the temperature is increased, this temperature-sensitive polymer or plastic that is in between the two conductors starts to soften. And that material is calibrated to soften at specific temperatures based on what the activation temperature is of the product. And as that's softening, the core conductors are coming closer together to one another. It's still at normal operation. Your signal is still going through the end-of-line resistor back to whatever it might be monitored by. But the cross-sectional view is the equivalent of an open circuit. Then as you reach your activation temperature, the insulative plastic melts to a point where those two core conductors touch one another. Once those touch one another, it creates a short circuit so that your system is only reading that new very low resistance value. It bypasses the end-of-line unit, and it is a short circuit, which we know will trip an alarm. So that's the basic operation of fixed temperature linear heat detection cable. It's been around a long time, and this is probably referred to as conventional linear heat detection. Each activation temperature is its own cable or own SKU or part number. The other variation of the product that we are offering, which is a bit unique, is called programmable temperature, LHD, sometimes called resistance sensing. And what this allows users to do is field adjust what the activation temperature will be. And it does this by constantly monitoring any minor changes in resistance. So as resistance is changing, the system and the algorithms will attribute a temperature to that resistance value. So there's a direct relationship between resistance and temperature. This allows for the controller to be able to allow the user to program your activation temperature between 129 Fahrenheit and 212 Fahrenheit is the UL listed temperature range. Another benefit with the programmable type is that it does not melt upon activation. As long as you stay below 257 degrees Fahrenheit, it is restorable / resettable. Nothing needs to be repaired physically. Why would linear heat detection be used in a project that might come across your desk or one that you might be bidding on? The obvious, required by a code or standard. This could also include engineering specifications. We know there are lots of different NFPA standards, and codes can be adopted with and without amendments. We're going to go into a few of those different codes today. Elevators, elevator shafts, we'll be talking about that, as well as a few others. What linear heat detection provides is continuous detection across the entire length of cable. So in areas where you have ceilings that are hard to get to, when you want to reduce the amount of electrical devices inside of a room, when you want just more efficient coverage in a room, in a space, typically linear heat detection is only going to be used when there is a ceiling. All of the codes are developed accordingly for when there is a ceiling in the room. It's also going to allow for much easier service and testing, which can come in handy in a lot of areas, especially elevator shafts, hazardous locations, and we'll go over various examples of that. They're highly resistant to environmental conditions, so this could include very low temperatures, like a cold storage warehouse with lots of airflow, places that are very damp and dusty. When looking at all the different types of detection devices, initiating devices that can be selected, many of them work in the optical frame. Optics don't do very well with a lot of these environmental factors, especially dust, moisture, sometimes even frost. So in certain applications, they can be the best for trouble-free operation. And also suitable for hazardous area locations. We'll go into that NFPA standard a little bit from NEC 70. It's essentially a passive wire, or it's designated as a simple apparatus. So the cable itself is good in almost all hazardous areas. So we'll go over some examples of that. You can also achieve closer proximity detection. And this could be overheat monitoring for equipment, machines, just more optimal detection location and detection times. So the top applications for linear heat detectors, you have road tunnels. This is in the NFPA standard, 502, I believe it is. And a lot of those environmental factors that we talked about, your dust, moisture, airflows, constant use, limited access, apply to road tunnels, as well as subway or underground train tunnels. You have your warehouse, which includes cold storage, as well as just storage, high-piled storage warehouses, and also sometimes in the racking itself. A lot of times these will be initiating devices for sprinkler release. Also, solar panels. These could be rooftop solar panels on a building. we've also had a couple of projects recently with solar farms, where it is a whole bunch of solar panels out in a field. And then honorable mention to cable trays, a lot more electrical transmission equipment throughout buildings, especially data centers, places like that. Another top application where linear heat detection is being considered more and more are parking structures. So these types of garages might have higher airflows. It might not be clear if they need detection, what type of detection would be best. Identifying what the hazards are, more high risk areas, all the different factors. A lot of these codes are being developed. We'll go over one example of a parking structure fire. Fixed or floating roof storage tanks, so mostly oil and gas related. Hazardous area location near the rim of the floating roof tank. We'll go over an example like that. And then also elevator shafts, which has become more and more of something that's being looked at for linear heat detection recently due to some new requirements in the NFPA 72 code as well as ASME A17.1. And we'll talk about elevator shafts specifically in a few slides from now. So there's going to be different challenges with every project. Environmental challenges for a cold storage warehouse. Obviously, you have the low temperatures. Not a lot of devices are rated or even suitable to go down into the negatives when it comes to negative C, negative F. So you have, just to begin with, very low ambient temperatures. Some of these cold storage, cold freezers can go down to negative 60 C, negative 40 C is pretty common. The ProReact, our linear heat detection cable, is rated down to negative 40 C, which also happens to be negative 40 F. And we have high confidence that it is suitable, even lower than that. With the humidity that are in these cold freezer, cold storage areas, they can be very susceptible to frost forming. So if you have an individual device, say a heat detector device, smoke detector device, sometimes these can just turn into a ball of frost or a ball of ice in these environments. So with linear heat detection cable, it is suitable for these environments. They do have an IP67 rating as well for ingress progression and moisture proof. Warehouses in general, they want to pack as much product, as much goods as they can vertically. So complex layouts, tight spaces, sometimes you can have highly flammable materials or hazards. A lot of times you'll have sprinkler lines, linear heat detection cable can run inside of the racks. And so you don't want any type of interruption from damaged cable, damaged sprinkler pipes. You want that to be set it and forget it, trouble-free operation in those areas. Linear heat detection is commonly used along the ceiling areas of these types of applications as well. And then for solar panels, obviously these are outdoors. Parts of the cable can get direct sunlight. You can try to have them shielded from direct sunlight. Also, another challenge is that the solar panels themselves, the surface temperatures can get so hot they can sometimes get 30 to 50 degrees hotter than whatever the ambient temperature of the air is, based on all that solar energy being absorbed. So depending on what your proximity is, that the cable is to your PV cells, could depend what that ambient temperature is and greatly affect your detection times. And most of the time, solar panels are on roofs, which don't get looked at too often. So having an automatic detection system can really help for stopping the spread of the fire. Usually these are caused and spread through electricity, and that can also be integrated with your building fire system. When talking about tunnels, lots of different environmental factors here. As we mentioned, dusty, damp, humid, could have very limited maintenance access, especially train tunnels. For road tunnels, an FPA 502 is the standard or the template for that. And it is noteworthy that NFPA 502 does require pinpoint location of a fire or an alarm within 50 feet. So it's important to note what your zone distances can be, or how to zone a tunnel, what your max distance might be based on how it's connected, which we'll go over some of those limitations later. But FFE's ProReact fixed temperature offers a very long max distance for cable length, as well as your alarm identification to satisfy this NFPA 502 requirement. Car parks, a lot of the same environmental factors. They can be lots of airflow as well when you have uncovered sides. Also, it's same kind of concept as warehouses. You want to fit as many cars as you can inside of a parking garage to maximize parking space. And then also we know that electric vehicles are more and more common nowadays, and fighting the fires from electric vehicles are their own battle, still constantly being developed in codes and standards. Floating roof tanks, likely going to need an EXD rated device or something suitable for that hazardous location. The detection is typically needed around the rim of that floating roof tank, which moves up and down as that liquid level changes. We'll show how this could be done, some common methods for doing so. You're going to have high ambient temperatures, fully outdoors, full sunlight, so similar to solar panels. So with elevator shafts specifically, or as they're referred to in the NFPA and ASME standards, shafts are also called hoistways. There is a new requirement in NFPA 72, the 2019 edition. And what this new requirement says is that all initiating devices for inside of the elevator shaft shall be required to be accessible for service, testing, and maintenance from outside of the elevator hoistway. I think the main reason for this requirement is that you needed highly trained and specialized service technicians to be able to ride the elevator car up and down, to be able to do the testing of any devices inside of that hoistway or shaft. So that was a safety concern for them. I know California, many states have already adopted and are enforcing this currently. So there's only a few ways to do that. Linear heat detection is a great way to do that. You can test from outside of the elevator shaft. Some of our beam smoke detectors, the fire array models, have been used in some of the 2 or 3 car elevator shafts for this purpose. Also, we've heard of aspirating models that can be used for this, but you may run into certain environmental factors such as the dustiness, humidity, so something to look out for there. It's also mentioned in the code that anytime you need an initiating device or just detection, say smoke detection is called for inside of an elevator shaft, it allows for other automatic fire detection initiating devices to be used instead, especially if the ambient conditions prohibit the installation. There's also a line that in the NFPA 72 code that smoke detectors shall be listed for the use in certain parts of the elevator shaft. And last I checked, there wasn't anything listed specifically for that. So I think that is still under development, and a lot of folks are using linear heat detection as a way to test from outside of the elevator shaft, as well as still have an initiating device in there that's not going to be prone to false alarms. So there's a couple of different functions that the linear heat detection could be initiating. One is power shutdown, or sometimes called shunt trip, for when you have sprinklers inside of the elevator hoistway. And the other function is recall. So we'll go over each one of those. And detection may be required inside of elevator shafts, whether it has sprinklers or not. So here, for the function of shutting off the elevator main power, this is also called shunt trip in a lot of the codes and standards. This function is going to be primarily or almost exclusively for elevator shafts with sprinklers in them. If it is a hydraulic type elevator, this will always have a sprinkler inside of the elevator shaft or hoistway. So you have this hydraulic equipment that is down at the bottom called the pit, and typically you'll have a sprinkler head down at the pit and some kind of detection. It could be a spot heat detector or it could be linear heat detection within 2 feet of that sprinkler head. So hydraulic will always have sprinklers. Also, in elevator shafts that are the traction type or the electronic type, those are for the mid-rise buildings, sometimes high-rise buildings. If there isn't a certain fire rating on the elevator hoistway itself, there could be sprinklers in there. So whenever there are sprinklers inside of an elevator hoistway, this is when your heat detection or your linear heat detection or some other type of initiating device is required for your power shutoff or your shunt trip. This is another device that does need to be tested from outside of the hoistway per that NFPA 72 2019 edition. So the idea between shutting off the power and having sprinklers is that you want to avoid a mixture of water from the sprinklers and the electronics from the elevator. So this is something that should alarm or trip several minutes before that sprinkler head is activated. And that's what is highlighted here in these code snippets. You have location, you have lower temperature rating, and a lower response time index as compared to the sprinklers to ensure that it does activate and shut off the power before water starts flowing. So there may be sprinklers located at the top, at the bottom, or both of the elevator shaft. For your electric traction elevators, they're going to have the controls, they're going to have the motor and gear drive equipment They could be located in different places, and we'll talk about that in the next couple slides here. But commonly, sprinkler activation temperature is around 200 degrees Fahrenheit, and your linear heat detection activation temp somewhere in the neighborhood between 129 to 155. Sometimes the sprinklers is a little higher activation temp, maybe somewhere in the 170s. And then the other function that these initiating devices may be initiating is phase 1 elevator recall. And what this is it's a process that is initiated that will take the passengers currently in the elevator and get them to a safe floor. So this is intended to occur minutes before the power shutdown, obviously, and also any sprinkler activation. And per NFPA 72 2019 edition, these different highlighted areas from the snippet are all going to have some kind of initiating device. If you have an elevator control room that is separate from the elevator shaft, then that's an easy one to test and do servicing on periodically or at your annual testing because it's in its own room. But sometimes what we're showing here on the right side is a machine room-less traction elevator, which are becoming more common. And this is where you have your traction machine and your different gears and equipment located inside of the elevator shaft. So requiring an initiating device for these specific pieces of equipment will also require you to have initiating devices inside of the hoistway that are also required to be tested from outside of the elevator shaft. So linear heat detection can be used wound up towards the top, also at the bottom if needed there. It can be for recall operation in non-sprinklered elevator shafts, as well as sprinklered elevator shafts. It can be used for recall as well as your power shutoff or your shunt trip operation. So now might be a good time if there are any questions. I didn't see any in the chat bubble, so I can proceed if not, but.
Yeah, we don't have any questions, Dean. Go ahead.
Okay, very good. So we did talk about warehouses and racking already. NFPA 13 is going to determine whether sprinklers are needed in a specific warehouse rack configuration. Linear heat detection could be used to release those lines prior to water flowing. So switching gears now to car parks, car garages. A couple of years ago, less than a couple of years ago, over in the UK where our headquarters is, the closest airport actually to where our products are manufactured, Luton Airport, they had a massive fire scenario at one of the parking garages. They think that it was initially detected by a passenger on an airplane who looked over out of the plane window and had seen the garage on fire. So by the time that crews had gotten there, over 100 firefighters, helicopters, and having it burn for 12 hours, huge impacts to not only flights being grounded, stranded passengers over 30,000, 24 hours of grounded flights, not to mention the cars that were destroyed, structural collapse. So we can see how just destructive that these fires can be in parking garages with mixes of electric vehicles as well as internal combustion engines. Also, 5 people were hospitalized in this incident. So obviously something everyone should want to prevent. And the British compliance body, BRE, had conducted a study that there is towards the first 5 to 10 minutes, even up to about 20 minutes, when you have scenarios like this, kind of a build-up period where your temperatures can be detected, like an overheat condition with linear heat detection, during these times to notify somebody that attention is needed in these areas, um, and potentially have saved this fire from becoming what it became and destroying all that it did. So linear heat detection is in the conversation with a lot of the development that's going on with codes and standards when it comes to parking structures. They can range wildly from garage to garage. They could be standalone, or they could be underneath buildings or right next to a building. There's different types of occupancies of those buildings. So a lot for them to get through, and a lot of that is in development now. Another popular application for linear heat detection are your aircraft hangars. NFPA 409 is the standard for that one. They mention heat detectors, fixed temperature, rate of rise, or rate compensation type. We offer the fixed temperature. And also it mentions flame detectors. Those have been used primarily to initiate the deluge systems for foam in a lot of these aircraft hangars over the last several decades. But after a comprehensive research study done by Pool Fire, it was realized that maybe having all of these flame detectors actuating a deluge of foam isn't the most effective approach. So a lot of hangars have gone a more holistic approach. They're still going to use flame detectors. Most of the time, they're still going to use linear heat detectors. It may be more reliant on performance-based fire protection engineering. But in that study that they had done of over 30 years of foam deluge dumps, it was found that the false alarms, most of those incidents, there were a few hundred incidents, most of those incidents were caused by false alarms, and the only fatalities that had occurred were from false alarm foam deluge dumps, and not actual fire scenarios. So a lot of that is also in development with flame detectors and linear heat detectors very much in the conversation. So looking at solar panels, we talked about some of the challenges with the environment as it relates to those, whether that's on a roof. We have different photos here. This top photo is from a Red Bull warehouse located near me in Phoenix, Arizona. That one, they deployed drones to get a sense for how big the fire was. Um, the bottom right photo here is that same Red Bull warehouse, showing just the amount of damage that had caused. So solar panels on roofs. Here's a little video here. Can be a challenge from a firefighting aspect, especially not having visibility of it, not knowing exactly what kind of damage it's doing to the structure of the roof, and getting it extinguished and stopping it from spreading. So earlier detection is a good idea, and linear heat detection is suitable for that environment. Also solar farms, like this one in the bottom right. This one also in Arizona, north of Phoenix, and it is one of a couple different projects that we know about using linear heat detection. Could be a deluge sprinkler setup, or it could be a pre-action type setup. But linear heat detection, if you are designing a system involving solar panels and linear heat detection, um, it's always good to do temperature modeling. It's always very good to know what the surface temperatures of the solar panel are going to be, to factor that into what your activation temperature is going to be. Typically, uh, the activation temperature is going to be at least 175 degrees Fahrenheit. Most of the time, maybe even 220, just based on these getting to an ambient temperature of 150 plus in some cases. So for your hazardous areas, um, the ProReact fixed temperature linear heat detection cable is declared by ATEX, the European directive, as a simple product, or a simple apparatus, as it's referred to in the NFPA standards. So that declaration exists because it is not cannot be a source for arcing. It's not carrying enough power, volts, amps combined, to cause arcing, to cause a spark. The only thing that you may have to look at is if your zone and your gas group have a very low ignition temperature, um, then whatever junction boxes that you're using, as well as the cable itself, making sure that that does not exceed the ignition temperature of that flammable gas. So snippet here on the bottom left of a simple apparatus shall be permitted to be installed in the hazardous locations as long as surface temperatures do not exceed the ignition temperature of the flammable gases. So on the right side, what we're showing is, on the right is hazardous area, on the left is safe area. Most of the time you're going to want your end-of-line resistor to be located in the safe area. It's easier usually to do testing in the safe area, and the end-of-line resistor is where you would do your testing. So this just leaves the cable itself in the hazardous area, but you can also have the end-of-line resistor in the hazardous area if you want. Intrinsically safe barriers and glands are typically recommended. It depends on the class and the division of your specific hazardous area. This shows the controller, which we'll go into more detail about, which can also be used as long as it's just the cable that is in the hazardous area, along with end-of-line junction boxes, intrinsically safe barriers, and glands. So in the top right here shows a floating roof tank. And since that roof tank is moving up and down based on the level of liquid inside of it, the detection needs to account for that somehow. And there are retractable cables that are commonly used for applications like this, kind of like a slinky. It allows it to move up and down. That retractable cable is a non-sensing cable. So this could be a 12, 14, 16, or 18 gauge wire, depending on the distance. And these are products that are available. And then your sensing cable is pictured in red around the rim of that floating roof. Then you can have your junction boxes in different places and your controller in a more safe area. The linear heat detection cable for the fixed temperature variation can also be connected directly to a panel or monitor module, but the controller allows you to have distance locating on your alarm point, as well as some different output options, so relays, RS-485 Modbus, etc. You can split off into 2 zones from the controller as well. Here's a little bit more about simple apparatus as it's defined in NEC 70. So different volts, amps, or watts, and how those are classified. And then linear heat detection is also a good choice in a lot of overheat monitoring type applications. So metal stamping or metal fabricating machines. This is a project that we did in the Chicago area, and you can see you have the metal fabricating equipment in which the insurance company was requiring additional detection closer to these machines. So our programmable linear heat detection was selected for this application, which we'll talk about here in a couple of minutes, which is overheat monitoring or temperature monitoring of these various different pieces of equipment or materials. So you got hydraulic pump skids, elevator traction equipment, as well as hazardous waste, nuclear wastes, things like that. So here is a table overview, which I hope you can appreciate. I know I'm a table person. I like to see the different products and their different characteristics all laid out on one screen. So your fixed temperature version is on the left, and your programmable temperature version is on the right. We have listings and approvals, the different activation temperatures that are available for fixed, 154F to 178, 190, 221, and 365. For your programmable, it's anywhere between 129 to 212. There is a rate of rise option with the programmable as well. It is kind of on the more drastic temperature increase side, at least as far as rate of rise is typically defined. 27 degrees Fahrenheit consistently for 3 minutes. So you need to have 81 degrees of temperature change for it to trip or for it to initiate this portion of the detection. Usually your ambient temperature is going to be close enough or less than 81 degrees below your activation temperature. So it might come in handy in, say, a freezer storage area for a little bit earlier detection, but note that that does have that. Your fixed temperature version is non-resettable, so that temperature sensitive polymer is actually melting upon activation. Once those 2 conductor cores touch, that area of cable needs to be replaced, usually about 10 feet on each side of wherever that activation occurred. You can do a splice in of a new length of cable. With your programmable temperature, as long as you're not reaching over 257 degrees, there's no need to replace that. Your fixed temperature can locate your alarm point. That's within a couple of feet. Your programmable does not have the ability to pinpoint the alarm point. Fixed temperature as well as programmable temperature, we offer standard with a nylon outer jacket material. This is going to provide a little bit better resistance against gasoline, especially, as well as a little bit better for direct sunlight. We also offer an upgraded stainless steel braided version. This is going to be over the regular PVC, which is most common for linear heat detection. So it's PVC with stainless steel braided over the top of that. So increased mechanical protection, high traffic areas, could be warehouse racking, place that might get beat up. So that's to prevent more damage. You have your zone length restrictions, or your min and max cable length. With your fixed, you're up to 10,000 feet. With your programmable, your zone length is up to 1,640 feet. Fixed flame or fixed temperature linear heat detection is suitable for your direct flame detection, because you only need a very small point along the cable to have those conductors touch and create that short circuit. While your programmable is more of taking more of the average temperature over the length. So if you did have a very hot spot along the length of the programmable temp version, you'd need at least 1% of whatever that zone is. So 1,600 foot long zone, you'd need at least 16 feet of that to be in that elevated temperature range. So the sensor cable itself, it's twisted trimetallic cores. So those three different metals are steel, tin, and copper. So that gives better conductivity than a lot of the common products out there. Lower resistance per foot, which could potentially, if you have IDC restrictions on how much resistance you can have, this could allow you to have longer lengths of cable. And we'll go into that in the next slide. But these are twisted and under constant pressure to come together. And once that temperature sensitive polymer is heated up, it will soften and allow those two to come together and create that short circuit. So as we mentioned, splicing in a new length of cable on 10 feet on either side of the alarm point is what needs to happen for the fixed temperature. So for fixed temperature linear heat detection by ProReact, a few different ways that you can connect this to your system. It can be connected directly to the fire panel. This is shown here in the top diagram. Also to your addressable monitors. Also, you have at the bottom here, we offer a ProReact fixed temperature controller. This is also called a digital interface monitor module, and we'll go into more detail here in a minute. But you have these three options on what to connect the cable directly to. You have so you have those three options where the cable is connected to, and then you also have a very low resistance compared to some other linear heat detection products on the market at 0.058 ohms per foot. So with Potter, I know that there might be an IDC cap that's advertised for devices not being over 100 ohms. Talking with James, he said that internally you guys have a rule that for linear heat detection, the max resistance or impedance DC is actually 700 ohms, and that applies to linear heat detection.
Yeah, I want to clarify that. I apologize.
Okay.
So on addressable modules and I/O circuits on our AFC and IPA panels, we're going to be limited to 100 ohms. We do have some panels with conventional circuits that were allowed 700 ohms. The 4410 G3 would be one of those panels that those IDC circuits would allow 700 ohms on. But most of our addressable equipment, that limitation is going to be 100 ohms. So
Great. Thanks for clarifying that, James. And so this slide will still stand for reference, if the max is 700 or if the max is 100, here's what those max cable lengths would be for that. But if you use the controller, you can go up to 10,000 feet. That would need it would need a 24 volt power source. So a little bit different than just attaching to the addressable module. And then also that controller can be monitored by an addressable module connected to the panel, obviously. Each of the ProReact fixed temperature controllers can handle up to 2 zones. And these separate zones are monitored, and there's a display readout that is going to give you either the status, or if there's an alarm situation, it will read out the distance. So that would be the distance from the controller that it gives, and so it's easy to see at what distance away, if you have that mapped out somewhere of this is what distance is what, you'll be able to know where the location of that alarm was. This says 50 meters, but it's also available in feet as well. Leader cables or non-sensing cables are just different gauges of 2-conductor wire. Depending on how long you want to go with your leader cable, you're going to use the appropriate gauge wire for that. And just looking closer at the controller for fixed temperature linear heat detection ProReact, also called digital interface monitor module. See a little bit better resolution view of what that display readout will look like. Also, you have your different indicator lights, alarm, fault, or trouble, shows that you're getting power. And then looking at the terminals inside of that controller, you have your 1 or 2 different zones. Power supply 1236 volts DC. It does have a Modbus RTU output if you want more of an analog type signal. There are also your alarm relays, relay terminals here, which can be monitored. So this is UL listed. It only draws about 6 milliamps at standby at 24 volts. And SIL 2 certificate of conformity for this. Another thing to point out that could come in handy with the controller is, with having 2 zones available, you can use 2 separate activation temperature products. So you can use, for instance, 154 activation as well as a 212 degree activation for the other one, and run them in parallel, and that way one of them can be more like a pre-alarm. It's more wiring, but it is something that is of interest to some folks. So now switching gears to the programmable linear heat detection version of ProReact. So this is different in that it is a 4-wire or 4-core sensor cable. We mentioned that it doesn't melt upon activation, but it has additional wires because it's referencing ambient temperature and it's monitoring for changes. So there's different calibration wires and your average temperature sensitive wires. It's the controller, which is required for the programmable type system, is doing the monitoring of the resistance levels between these 4 wires to determine what the temperature is. It's also compensating for periodic changes in ambient temperature. And you are able to select the activation temperature via this controller in the field, anywhere between 129 to 212 degrees Fahrenheit per the UL listing. So here's what a setup might look like using the programmable linear heat detection product. You have a separate power supply here. You have your control module, and then linear heat detection cable inside of the zone, as well as end-of-line unit. So this is also suitable for hazardous locations. Always a good idea to use intrinsically safe barriers for any penetrations. Also, if your end of line is in the hazardous area, glands as well as barriers, seals. And a closer look here at the programmable control unit. Self-contained, and you have the option to program it with a laptop if that's your preference, or everything can be done just on the controller itself. So one of the first steps is programming the ambient temperature to have it set for that. We have instructions and software and everything that anyone would need for this. It has the Modbus RS485 output, as well as relay contacts for your alarm and trouble. It is important to note that only one zone of cable per controller is to be used for this. There's also an event log going back 3 alarm incidents. And then we talked a little bit about the rate of rise function, which is pretty drastic. There would need to be a pretty quick rise for 3 straight minutes, and it's usually only going to come in handy if your ambient temperature is much, much lower than your activation temperature to serve the purpose of earlier detection. But that is an option to be programmed on the controller. And this goes for both versions, both fixed and programmable. Our standard outer jacket material is nylon. You can see the chemical resistance for nylon versus PVC. We can also still provide PVC if that is more desired or required for certain things. But nylon does have a little bit better mechanical protection, direct sunlight, as well as gasoline. And then stainless steel braided, which is over a PVC, is an armoring material, so it's going to give obvious mechanical benefits when it comes to fork trucks, different damage that can occur in the field. There's one UL test that's used for all different types of cables, where a propane burner is used and the flame is put directly onto the cable. Some of the results are used to show response time to activation of the fixed temperature product. So this is essentially a temperature quench where it reaches temperature very quickly, and the lag or the delay once it reaches that temperature is going to range between 8 and 13 seconds based on these results. Ambient temperatures and what the ambient temperature maximum could end up being in your application is going to be something to really pay attention to and really factor into what your activation temperature is going to be. Usually, for the fixed product, fixed temperature version of ProReact, whatever your max ambient temperature is going to be, say it's an elevator shaft and it could get to 100 degrees Fahrenheit, it's recommended to be at least 29 or so degrees above whatever that is. UL and FM, they're both testing, they both have test procedures where they take the ambient temperature of the detector to within about 10 or 20 degrees below the activation temperature. So a lot of this test procedure is for spot heat detectors, but they do run some of the linear heat detection products through this as well. This table here is for spot heats, but you can see that usually your max ambient temperature is going to be 20 degrees or more below the activation temperature. So here's just to go into more detail about what exactly is UL testing and what exactly is FM testing. So ProReact fixed version has both UL and FM approvals and listings. The programmable product, it has UL only for now. Working on the FM, we don't have a timeline for that yet. But here's just an overview of what UL is testing for linear heat detection as well as spot heat detection. So there's an oven test, and the devices should initiate or alarm in under 2 minutes from when it reaches the temperature inside the oven. There's also a live fire test, and the diagram on the right shows the layout of that. You have your different spacing values for either spot heats or linear heat. Linear heat is going to look more like this, oriented in the test chamber. So this is a 60-foot by 60-foot test chamber. I think with a 15-foot high ceiling. They also do a high ambient temperature test, which I mentioned before. For UL, it's 10 to 20 below activation temp. For FM, it is 10% below, so it's still going to be around the same. Your rate of rise, that can be manufacturer defined per UL, but with FM, they have it strictly defined between 15 to 25 degrees Fahrenheit per minute. Their UL does include a low temperature exposure test where they have it at negative 22 degrees Fahrenheit for 24 hours. I think that then they do a test afterwards to make sure it works. And they also do have a few different corrosion tests in UL 521. So just for reference, UL 521 is about 129 pages of all the different tests that they put these different devices through. FM 3210, I think, is only about 30 pages long or so. So not UL by comparison is putting it through a lot more paces for from the testing aspects. And FM 3210 plunge tunnel is similar to the oven test that's done by UL, and you have no low temperature test and no corrosion tests. But note that FM does have a lot of data sheets for specific applications. So those might have different requirements for different devices, say, like their cold storage FM data sheet, freezer storage. They might have different requirements where stuff needs to be suitable for different environments or be able to perform for different things. So NFPA 72 guidance for heat detection. Location of the devices is on the ceiling or on sidewalls, not more than 20 inches from the ceiling. So mounting height is pretty simple when it comes to linear heat detection. No more than 20 inches below the ceiling. per NFPA. As far as how close to the ceiling can you get with your mounting height, our manufacturer recommendation is at least about 3/4 of an inch below the ceiling. So that gives you about 19 inches of mounting height to play with there. And the reason that it's a little bit off the ceiling is because you don't want the ceiling to be absorbing a lot of that heat, and you want the cable to be absorbing the heat from the hot gases from all sides for optimal detection time. So a lot of people, myself included, might look at NFPA 72, Chapter 17, look at how to space heat detectors, and think that anything over 10-foot high ceilings, you need to tighten up your spacing. This table in Chapter 17 is only for spot detectors. Linear heat detectors are treated separately. If you go a couple of lines down, for line type detectors, the D rating required by this table shall not apply. So usually, linear heat detection products are going to have a listed spacing for area coverage. And this might vary by product, by manufacturer. And that's going to give you what your max distance between your cable runs can be. So for area coverage applications, the spacing between parallel runs is typically determined by the product's listed spacing value. So for a lot of the ProReact products, it is 35-foot listed spacing for UL, or 30-foot FM spacing for FM. And what this means is that your space in between cable runs here is either going to be 35 feet or 30 feet anytime your ceiling height is 30 feet or less. We have a general recommendation that above 30 feet ceiling height, you cut that spacing in half. So double up the amount of linear heat detection cable you have for any ceiling heights over 30 feet. So here's a little NFPA 72 snippet. Shall not exceed the listed spacing. Pretty straightforward. You have half of that spacing value to the wall. And then your distance from the ceiling, as we mentioned in the last slide, 0.8 inches to 28 inches down from the ceiling. Then towards your corners, they have what's called the 0.7 rule. And as long as you're sticking with your spacing from walls, you should be good with your 0.7 spacing rule. When dealing with slope ceilings, which means that the slope of the ceiling has a rise over run of more than 1 in 8, a heat detector cable run has to be within 3 feet of the peak, which could be for this peak type roof or this shed type roof, within 3 feet of the peak, which is where all the hot gases will be going as they rise up in the space. And some general do's and don'ts and best practices. If the cable might be subject to very different ambient temperatures along the path, usually fixed temperature is best here. There's also leader cables that can be used if you have a hot area, then a cold area, then a hot area, and things like that. So the non-sensing cables can come in handy, especially if the controller is far from the space that's being protected. Also, if you need alarm point distance location, your fixed temperature is the only one of the products that we offer that can do that. So programmable would not be a good choice in that instance, say for a road tunnel. unless you had it zoned properly for every 50-foot by 50-foot space. So T-spurs are not recommended. Also, there is a minimum bending radius of 2 inches anytime you're making a 90. It's good practice you could test the resistance of the cable on the reel for starting. And also always take into account what the maximum ambient temperature is going to be for your application when determining what the activation temperature will be. So various accessories that we offer, V, L, J, and P clips. Also special nylon zip ties, end-of-line junction boxes, end-of-line test stations for the fixed version, which we'll go into in the testing section right after this slide. For NFPA 72, you have a visual inspection frequency of twice a year or semi-annually, and you have a testing requirement of annually for your frequency for linear heat detectors. And in our literature, we have what to check for the visual inspection. So we do offer an end-of-line test station, which makes it as easy as pressing a button to perform your testing. If you put this in a more preferred location, like outside of an elevator shaft, even better. If you have the end-of-line test unit, the fixed temperature version, you just use the switch for alarm, and there's one for each zone. There's also a switch for testing your trouble as well. If you do not have an end-of-line test unit and it's just a junction box, say with a end-of-line resistor, you can test it by shorting the end-of-line or disconnecting the cable for trouble, and then you have your estimated or your ohms per foot, which comes out to about 0.058 loop resistance per foot. So 0.058 ohms per foot loop. So that takes into account both legs. For the programmable version, while you're connected to the panel, the procedure is a little bit different than if you're disconnected from the panel. But you just use a 1 mega ohm resistor across the 2 clear cores. That should give it an alarm. If you're disconnected from the panel, then all you're doing is measuring resistance between a few of the different terminals or wires, I should say. So that wraps up what I have for you. I didn't see any more questions or anything, but I'll stick around as long as we need if there are any questions.
Hey, Dean, real quick. Let's talk about what you had referred to as the conventional linear heat detection cable. Is there a way that you can easily visually see where that alarm has been caused? My assumption would be that outer jacket would also melt away just like the inner jacket would, allowing that short to occur. Would that be correct?
Yeah, especially if there was a fire, the outer is gonna melt along with that. If it's more of like a machine overheat type scenario, it might be more subtle. But yeah, there will be clues for sure. And I wouldn't, if you're going to be relying on your linear heat detection cable to help you determine exactly where a fire event happened from, I wouldn't rely on it solely. I'd look for other things to try to investigate that, but usually there are some pretty obvious signs.
And it also appears here too that you can do the old I'll refer to it as the NEC trick. You can meter the resistance across those legs, and that'll give you the approximate distance from where you're at. So.
Yeah, exactly. Good point.
Okay, well, it appears that we don't have any questions. So, unless you have anything else for us, Dean, we'll go ahead and wrap this up. I would like to thank FFE and Dan Russian for presenting this material today. Very informative, very in depth. Thank you very much, sir.
All right. Thank you, James.
For more information about Potter products, please visit our website at pottersignal.com. To access additional training resources, check out our online training portal at academy.pottersignal.com. Stay connected with us on social media for the latest updates and news.